I went over the tests. I handed those back. We went over them. I took up comments, questions, concerns. We put them back in the folders. I got the folders back up here. If you were away yesterday and didn't see your test, come see me tomorrow at lunch. You can go through it then. And then we moved on to the next chapter, Unit 3 here, dynamics and momentum. We started talking about forces, what they are. We have kind of a vague-ish definition of here, which does work. Brad gave it to us. I gave us the units. The units of forces are newtons, named after the guy. Isaac Newton was the guy responsible for all of this. If you're on your phone, put it away, Harleen. Please and thank you. And so he's the guy that gets honored with the unit. There are 4 fundamental forces that make up all of the forces in the universe. We talked about those: gravity, electromagnetic, strong nuclear force, and weak nuclear force. And then I went through a list of, there's all sorts of forces that act in our world. Most of them can get dropped down to one of these. We talked about them, what they are, how they interact in life, and now we're going to move on to something called a free body diagram. So the forces that we listed are gravity. All of them I gave notation for. Gravity is Fg, your normal force is Fn. Gravity and normal are the most common ones that we will be dealing with. Gravity, obviously, Brad, put your phone away, exists on any planet or moon that you will find yourself on. Normal force exists whenever you are in contact with a surface. It doesn't matter what that surface is. Could be a wall, floor, chair, whatever. As soon as you are in contact with a surface, you're going to experience a normal force, and that normal force is 90 degrees perpendicular to whatever surface you're interacting with. Friction is caused by the interlocking rough surfaces, drag, elastic force, tension force, buoyancy, which we're not really going to talk about, but it's important to acknowledge because every time anyone who's ever sat in a pool or bathtub, lake, ocean, whatever, you've experienced buoyancy to a degree. And then the applied force. Applied force is just a catch-all force. If you can call it something else, then call it something else. But if you have no other good name for a force acting on an object, you can just lump it into an applied force. And as long as you acknowledge that it's there, it doesn't matter. So where we start as we go forth and look at all of these kinds of dynamics situations, the place we start with everything is what's called a free body diagram. And a free body diagram it's just the body, the object that's experiencing whatever is being discussed in a particular problem, and the forces that are acting on it. Just the forces that are acting on it. So to use and keep track of all these forces involved in a particular situation, we use what's called a free body diagram. Will now forever be abbreviated as an FBD. And I'll give you a couple examples, and then I'll give you some situations to play with. So if a box is being pushed across a rough floor at a constant velocity, what's the free body diagram? So there's the box. If it helps, you don't have to, but if it helps, I shouldn't say you don't have to. If there are surfaces, let's include those surfaces wherever they happen to be. So if a box is being pushed across a rough floor, let's add the floor. There's the floor. And just like when we were dealing with kinematics, in dynamics, the words that are used to describe what's going on have a deeper meaning. So a box is being pushed across a rough floor at constant velocity. There are 3 words in there that are implying things. What are they? Yes. Pushed. Pushed is one. Pushed implies the existence of something. Don't know what it is. Could be a person, could be a car, could be a dog, I don't know. Moving this box across the floor. We don't know what it is. Let's toss it into the catch-all. This is where we would include an FA. So again, we don't know if it's left. We don't know if it's to the right. We know it's across the floor. Generally, I would assume that this thing is moving to the right, but you don't have to. So Emma, you identified the applied force, the pushed. Which way do you want it to go? Sure. So on the drawing, Everything gets labeled from the center of mass. So from the center of mass, which is usually in the objects that we look at, it's in the middle. Out from the center of mass in the direction that the thing's acting in, we draw an arrow to signify that we haven't labeled it, but forces are vectors. They act in particular directions. I probably should have included that as part of your definition up at the top, but know here now, forces have directions and magnitudes. They are vectors. Okay, that's one word. What's another one? Yeah, Akai. Rough. Rough implies friction. So, talking about friction, we haven't talked about it in a lot of detail yet, but what do you know about friction? Which way would you expect friction to be acting in this scenario? Yeah, to the left. We said earlier that friction is caused by interlocking rough surfaces. So there would be a rough surface between the bottom of the box and the floor. And if you're pushing to the right, friction is going to oppose you. Did we say that up here? We didn't. So let's add that. Let's go back up here and add that. Up where it says, or we've got friction caused by interlocking rough surface, says I should have had that added yesterday, and I'm sorry I didn't. Friction always opposes motion. So we've got our applied force to the right. Emma decided it was to the right for totally arbitrary reasons. Friction has to be to the left because it's going to oppose the motion here. There is another word in here that is going to give us another force. Yeah, Emma. That implies something else. Can we come back to that? There's another word here that implies the existence of another force. Actually, two other forces. Brad, you were going to put your hand up a second ago. Yeah. Same thing. Okay. Emma, you got another one? What word in here implies the existence of the normal force? You're right. What word implies that? Now, pushing implies the FA. Nope. If we go back up here to look at what a normal force actually was, and acts whenever you're in contact with the surface, what's the surface in this question? The floor. That implies the existence of the normal force, and the normal force acts 90 degrees to the floor. So that one's going to go straight up. That's your normal force. The floor, though, also implies the existence of another one. Floor also implies what? Henry, gravity. Gravity always acts straight down. If you don't have gravity, it doesn't make sense to call the floor. Because if just gravity ceased to exist and we were floating around inside this room, any of the surfaces could reasonably considered to be the floor. If there's no gravity, up doesn't make sense. So the fact that we're calling it the floor means FG exists and is down. Cool. Let's go back to constant velocity. Emma, you suggested it first. What does constant velocity imply? No, bring it back here. This is different. Ignore. It's moving at constant velocity. Yeah. What else does it imply? What's not changing? So what does that mean? You got it wrong on your test, you're going to get it right here. Yeah. Keep going. Velocity is not changing, which means something is zero. I'm looking right at you. You don't have to put your hand up. Don't ask Raina. Velocity is not changing. Means something's equal to zero. What is equal to zero? No. Raina? Brad? You had your hand up a second ago about it too. Constant velocity implies what? You're next if he doesn't get it. Nope. Brad, you can pass to if you'd like. Ezra wants to take it. Acceleration 0. Constant velocity means A is equal to 0. If the acceleration is equal to 0, there is another assumption here that Emma, you gave us yesterday. You said an unbalanced force causes an acceleration. That is true. You are moving right now at constant velocity. Go do what you got to do, Christian. You are moving at constant velocity right now. Your velocity just happens to be 0. The reason that you have no acceleration and you're not moving and therefore have no acceleration is because the forces on you are, you said it yesterday, I'm going to say it again today. Starts with a B. Ezra, Henry. Balanced, Henry. Forces are balanced. The constant velocity implies acceleration equals 0. Acceleration equals 0 means the forces, yes, I would love nothing more than to have you actually see what I'm writing. Forces are balanced. If the forces are balanced, what is the implication? Look at the forces we have labeled. Which ones have to be balanced if we're moving at constant velocity? Ezra, you have a smile on your face that says you know the answer. Normal and gravity, those two must be equal and opposite. If they're not, object is getting either launched up off the ground, which isn't happening, or gravity is sucking it down into the ground, also not happening. You guys are comfortably, well, maybe not comfortably, you guys are sitting in a chair, not being sucked into the chair, you're just, kind of on it. Gravity's pulling you down, chair is pushing up, you're not getting flung into the sky or sucked into the ground, which means those forces have to be equal and opposite. But if you are moving constant velocity, if you're moving to the right due to this applied force, but you're moving at a constant velocity, which means you have no acceleration. If there's no acceleration, then the forces are balanced. What other set of forces have to be equal? FA and FF. These two also must be equal and opposite. There is so much baked into a box is pushed across a rough floor at constant velocity. The math here is going to get easier than it was. But this conceptually, the physics is going to get, it's dense. There is a richness to the sentence that is going to piss a lot of you off, I think. But that's why you're here. That's why you're taking Physics 11. So this is what the free body diagram would look like. Just these forces, the purple, green, and the two brown ones, and the existence of the floor. That's the free body diagram. So the next one, a hockey player glides on a frictionless ice at a constant velocity. It's on ice. Let's draw the surface. There's the ice. Talk to me about forces that are acting here. Ice implies the surface. Brad.
Friction and applied force because he's pushing himself as he glides. He's pushing himself to the ice. He's pushing his body across the ice.
You sure?
Yeah, I said friction at first, but then also isn't there
also, okay.
Applied force from himself, isn't there?
Is there?
He's moving,
so there's at some point, you're right. If he's moving, because it says he's moving, At some point, something had to have started him moving. But what are we drawing the free body diagram for? And this is going to be the super irritating part. The danger is, here, the danger was not assuming enough. Not knowing how to read into the language of the problem. Here, in example 2, the danger is assuming too much. Because Brad, you're not wrong. At some point, something had to start this hockey player. Don't know what it was. Could have been, let's say I'm on the bench, because I can't skate. I was the kid who sat on the bench. Whenever my elementary school went skating, as soon as I could get into the penalty box, I was in the penalty box. I hated skating. It's cold, hurts when you fall. Why would I want to do this? So maybe I'm in the penalty box and you're there on the ice and I pushed you. Maybe that's why you're gliding. I don't know. Maybe you pushed off. Maybe that's why you're gliding. I don't know. But that's not what we're drawing the free body diagram for. The hockey player, at some point in the past that may have happened, you open your eyes, you are blind, but now you see, and all you see is the hockey player gliding across the ice. In that moment, is there an applied force acting? No. Because it's not specified, we can't assume it. Even though we know it happened at some point, in this image, it's not there. Emma, you also said, he said friction, you said it's frictionless. This force of friction equals 0. If the force of friction equals 0 and the skater is moving at constant velocity, it means that, like if we looked over here, if we had friction, constant velocity implied that these two are equal. If there is a constant velocity and there's no friction, it means there's nothing else pushing it forward either. It can't be, because otherwise it's not constant velocity. The pushing is what gives you the acceleration. So there's no force of friction, and this glides implies Fa equals 0 as well. There's no applied force. So then for a hockey player that's gliding on ice, what are the only two forces that we can draw here? Gravity's one. Normal's the other. Fn, Fg. And there is movement. Let's make a note of that. We know there's movement. But just because there's movement doesn't mean that there's a force right now causing the movement. Some point in the past. We don't care about the past. We live in the now. Questions, comments, concerns? Hashtag no regrets. That's not true. Regret things. Okay. So, I have 8 things here. I would like you with, all of you are sitting with someone except Kai. Discuss these 8 things. I want you to draw them. I want free body diagrams for all 8 situations here. I don't want you to do them alone. So Kai, move somewhere. Talk to someone. I don't care where you go. Discuss with someone you respect what forces are acting on each object in these given scenarios, and we'll take them up as a class in a little bit. On your markets, I go.
Dude, I'm like super comfy right now. Super duper.
Super duper comfy?
Yeah.
Okay, then you can wait for Marcos. Or you can convince Brad to join you. If you can, and I would go so far as to say, if you are creating a fantastic work of art, make sure that the fantastic work of art is not impeding your understanding of the problem. When we get to the question I'm referring to, I'll show you. Okay, so we've got a book is at rest on a tabletop. Here's tabletop. Here's book. What forces are acting on the book? Gravity, someone said, from the center down. Fg. And then normal. That's it. There's no, while we would say that friction is a thing, it is not, at this point, friction is not acting. Friction is only going to start to engage with the book when you try and move the book. An object at rest is not going to experience friction. Okay, let's go to the right, I guess. Number 5. A rightward force is applied to a book in order to accelerate it across a desk. Here's the desk. What forces are acting on the book? Gravity. Brad. Normal. Normal's which way? Straight up. Anytime you're in contact with a surface, you experience a normal force. What other forces are acting? Applied. I'm assuming you're cool with me drawing it to the right because it's at a rightward force. I'm assuming that's what you're referring to, Jack. And Raina? Friction. And just so we're clear, which two forces here are equal and which two forces here are not? Gravity and normal are equal because the book's not being flung up or down. The unequal ones are? I don't know if you're Snapchatting or on Instagram, but you don't need to do either of those things. Draw the things. Friction and the FA, the applied force, whatever it is. Okay, that's the free body diagram. Love it. 2, a girl sits on a swing that is, not it, that is attached to the frame by 2 ropes. So there was some discussion as to how you would draw this. What are the objects that we're actually going to include here? And it seems like you guys came to a consensus that we're doing it all. So let's do it all, I suppose. Here's my swing. Well, the consensus was formed informally when I walked around and saw everybody did basically the same thing. If you do it this way, there's my swing attached by ropes, and here's the girl. There she is. You do not have to get more artistically involved than that. You can assume people are blocks in physics. In fact, I encourage it. So what forces are acting on everything there? If we, and some people included the frame. Okay, so if you include the frame, now there's more forces to include. The more you include, the more you have to therefore label. So based on that, girl on swing attached by ropes or with ropes to frame, what forces are acting on this mess? Tension in the ropes. Where? Emma. Down on both sides where the frame is, and up on both sides where it attaches to the swing. You bet. And now you've got, if you have multiple forces being labeled here, we have to label them assuming they're not the same. So we're going to go FT over, I'll call this FT1, I'll call this FT2. We haven't talked about tension in more detail than just what we've done so far. But one thing I will tell you, Raina, your answer to where is the tension, you said, I don't know, just kind of in the ropes, is actually the best answer you could have possibly given, because that's totally true. It's just kind of everywhere in the rope, and every single part of the rope experiences tension in both directions. So down here, we're at this end, it's up, at this end, it's down, but otherwise these two are going to be equal and opposite. So this is FT2 and this is also FT2. This is also going to be FT1 because this is FT1, it's the same rope. Unknowingly, perhaps, Raina, your description was perfect. So what other forces are acting? We've got the tensions in the ropes. Gravity, love gravity. Gravity on what? Just the swing, okay. There's FG. Oh, and the girl. So from her center of mass, we need to draw another gravity. I'll call her gravity FG1 and the swing's gravity FG2. They are not the same. And what other forces acting? Are there any other forces acting? Normal force, where? On the human? Well, we know it's a girl, so you can get more specifically than saying human. On the girl from what? What surface is she in contact with if there's a normal force? The swing. That's everything. Who thought sitting on a swing could be so complicated? That's the free body diagram for girl on a swing attached to frame by ropes. Questions about that ugly monstrosity? Did anyone draw anything differently that you wanted to talk about? Did anyone make any different assumptions? If you said, well, forget all that, I just want to talk about the girl on the swing. If you're just talking about girl on swing, what forces are you going to label for girl on swing? Here's girl on swing. Gravity. And normal. She's in contact with swing. If you're talking about the entire scenario, that's what you draw. If you're isolating it to girl on swing, that's all you have to draw. Cool. Skydiver, falling, constant velocity. The degree to which you draw the person, some of you drew fantastic people. I am not as skilled as you. Here's my person. You could draw them like a box. And I like to draw speed lines. There's our person falling towards the ground. What forces are acting on skydiver falling with constant velocity? Gravity. And the only way that a skydiver could fall with constant velocity is if what is also here? Drag. Constant velocity implies they're not accelerating. If gravity's acting down, something has to be acting up. And in this case, it's going to be drag. F, drag. And I think I said it before, I don't know if you all heard me. This is actually an accurate representation of what it means to skydive. Those of you who have never been, there is a maximum velocity that you will reach. It's called terminal velocity. It's different depending on your orientation. If you want to be Tom Cruise in Mission Impossible and go faster, you point yourself straight down. If you are terrified of the whole experience and want to go slower, you go like a flying squirrel. Okay, 3, an egg. Let's go faster because we only have 4 minutes left. There's my egg. Free body diagram. Gravity. If we're neglecting air resistance, that's it, we're done. Football. There's my football. Being punted, it's already been punted. The booting has happened at some point in the past. What's the free body diagram going to look like? If we neglect air resistance, just gravity. Straight down. We can put some speed lines demonstrating which way these things are moving. But the only forces in both of these is gravity. Okay, plane. Here's my plane. There's my plane. What forces are acting on the plane? List them all. We only have lift is up.
And gravity down.
You bet. Otherwise, it flies up into space.
Forward is FA.
From the engines, yes, an applied force. Back is drag. Crushed it. Don't pack up. We got one more left. Bell hasn't gone yet. Number 8. A car is coasting to the right. Yes.
Drag right.
Hold on. Car. There's car. Drag is acting to the right. Why? Is it? Let's draw the ones we're not going to argue about. The ones that we're not going to argue about are what?
Normal.
Normal up and gravity down.
Wait, could they do both then? Like both friction from the road and like air resistance?
It's the brakes are not locked. Is there going to be friction on the road from the road? There's friction on the bearings of the wheels themselves, but it's not going to be from the road. Like, we got to be real specific about what's going on here. But yes, there is a friction force backwards. Something has to be slowing this thing down as it's moving to the right. You could break up and call it drag and friction, because both of those things are going to exist. The air is going to slow it down. The friction on the bearings inside is going to slow this thing down. But those are not going to be to the right. They're going to be to the left, because the car is moving to the right, but it's slowing down. This word coasting implies that the engine is not, the drive at least is not engaged, and you're not braking. Coasting implies no engine and no brake. Okay, there you go. He had to go pick up his backpack. Okay. When the bell goes, you may also go. Have a super duper day. Oh, what timing. Look at me go.
Tomorrow is the last day, so we should just watch a movie.
Not a chance.
We could have at least thought about it.
I have thought about it every other time it's been discussed.
Is someone gonna leave stink bombs in here again?
Nope,
It smells like eggs.
I don't smell any eggs.
Try these.
Smell like at the beginning of class.
Could be the grade 9s in here. Could be the grade 9s in here from last block.
Yeah.
Probably just got used to it.
Do you film your lessons?
I do.